So it's a real pleasure to be here in this wonderful venue and to conclude this session. So I will try to. This is a work in progress, first of all. I'm working on this together with Florio Chaya and Alberto Ibor, Seppe Marmon, and the group in Madrid. So what I will try to present you in this presentation are just some reflection on the notion of transition that are connected to a novel approach to quantum mechanics that we are developing in the last years, using as a central object the concept of groupoids. This type of description was inspired by the work by Schwingers. In his idea, quantum mechanics deserved a new symbolic language for better describing in a more suitable way the contents of quantum mechanics, and introduced this idea of selective measurements, which are devices connecting different states of a certain system, using this as a building block. And what we have interpreted in the last year is this concept in terms of morphism of groupoid and the groupoid algebra. So what I'm going to present you today is some interpretation of these quantities from a more logical perspective, and I will try to explain in what sense is logical. So first of all, I will start from the papers by Birkhoff and von Neumann by reviewing briefly this paper on the logic of quantum mechanics. Then I will try to move to the groupoid setting and introducing a notion of which we are calling conditionality, but maybe a better name could be found. And in the end, I will try to introduce R measure in order to give a statistical interpretation for this quantity, for this relation. Okay, so the logic of quantum mechanics. In this paper in 1936, Birkhoff and von Neumann introduced the set, started from the set of experimental propositions in order to describe a physical system. This set of experimental propositions must have certain properties and relation and operation, which made him, first of all, an orthocomplemental lattice. We have an order relation, which according to their interpretation, it represents the material implication among propositions. And there are two operations, which are the join and emit connected to this order relation. And then there is always a proposition which is true and one which is false. And for every proposition, we have its complement. From this point of view, this description is general, both for classical and quantum system. However, they were able to find some property which distinguishes the two cases, which is the distributivity property of the join with respect to the meet, which made it a Boolean lattice. Here we recover basically the measure theory and probability theory, the usual interpretation of probability theory. Indeed, the basic example is the power set of a set gamma. In all these settings, I will stay in the finite dimensional, in the finite set. So all the sets that I will go to consider are finite and discrete sets. So just to avoid any complication. However, we can relax this condition of distributivity, and what they consider actually, when Birkhoff considered, was the modular property, which is a sort of weakened distributivity only when A is a subset of C. With this modular lattice, what they proved is that the basic example of modular lattice is the set of all closed subspaces, vector subspaces of a Hilbert space. So they were able to recover the quantum case in this setting. And the main theorem that they proved that basically every finite orthocomplemented modular lattice is the product of a classical part and a quantum part. Why modular? But however, this setting cannot be extended to the infinite dimensional setting. Already was mentioned by von Neumann in that paper. But why he wanted to maintain these properties? Because it is equivalent to the existence of a dimension function, which is a sort of universal measure on the proposition, on the set of proposition. He was interested in this property in order to give us a frequentistic interpretation of probability, like a way to counting. So for the states of quantum in quantum mechanics. Another relation that one can consider among propositions is the compatibility relation. Basically, two propositions are compatible if one can be recovered from the other, according to this relation. How can we induce any statistical interpretation now on this set of propositions? Well, using states, which are basically functionals on the set of propositions with values in the reals, which must be monotone and additive, but only when we consider a join of compatible propositions. In the Boolean case, all the propositions are compatible, and so we recover the usual notion of measure. But in the quantum case, this is not the case, and indeed, with the Gleason theorem, we are able to recover all the density matrices in this setting, at least for the finite case. Okay, but what groupoids add to this setting? Okay, so a groupoid is so first of all, I will introduce what is a groupoid. It's a set of morphism, is all this environment, basically. There is a set of objects, and for every morphism, we associate via source and a target map a pairs of objects. A second property that we have on the groupoid is the composability, a partial composition law. We can introduce a subset of the pair of morphism, and this composition is associative. For every object, there is a unit, and every morphism has an inverse. In the Schwinger approach to quantum mechanics, we interpret this morphism as a transition, as atomic transition, we can say. And now I will try to explain in which sense they are atomic transition. And okay, so this is a generalization of groups. Indeed, groups are groupoids. In this case, the units, it's only one. It's only the unit. All morphisms can be composed among themselves according to the group law, and every group element has an inverse in it. Finite set are a trivial group, or can be interpreted as a trivial groupoid, where we have only units. But we can consider also groupoid of pairs. In this case, we have pairs of elements of a set, and the pair ij can be composed with the pair jk, giving the pair ik. Okay, so how can we connect this with the previous approach in terms of lattices? Well, since we have this set, we can consider the power set of every Boolean lattice in this groupoid, in this set. But due to the presence of the composition law and the inversion on the groupoid, we induce additional relation and additional operation on the set of proposition. Indeed, we have a multiplication law. Basically, we have a set B and a set A, and we construct a new set which is made up of all the composition of elements, one from B and one from A. This composition is distributed with respect to the join and the meet. And when we consider sets C and B such that the target, the image of via the target is disjoint, the disjointness is preserved. Okay, so another operation is the inverse, which to every element, to every set, associate the set made of all the inverses of the transition, of the morphism. How can we use this? Well, we can use all these ingredients to consider a relation which we call conditionality, saying that basically if we take A and B, which are propositions now from the set of all propositions in the set of objects, B in its relation is conditional to A, if this set is different from the empty set. This relation is, one can show that it is reflexive and symmetric, but it's not transitive. And we can see that we are using actually all the ingredients in the groupoid. Basic example, well, when we have the trivial set, we have local conditionals because the set B and the set A are conditional if they have a non-empty intersection. But if I consider groupoid of pairs, and I take two atoms, any pair of atoms, they have an empty intersection. However, every pair of atoms is conditional. So in this sense, we are introducing a sort of non-local conditionals. This actually was interesting for us because we used this model as basic model for a finite dimensional quantum system in the Schwinger approach to quantum mechanics. Now we are moving to the statistical interpretation considering functionals on this set. So we are going to introduce measure, but since we have a composition and an inversion, we are looking for measures that are compatible with this operation. And in this sense, we can generalize the notion of R measure for groups to groupoids using a family of measure indexed by the by objects. And every of this family of, so if we consider the pre-image of via the target map of every point x, y of every object, we have a leaf, and on this leaf we can support, the measure that we are considering is supported on this leaf, and all these measures are joined, are connected by a measure on the space of objects. We are asking for left invariance, means that when we act with the groupoid on itself, we are moving the measure from one leaf to the other. And we are asking also for a compatibility relation with the inversion, which makes appear this delta function, which is called the modular function. This is a groupoid homomorphism, and this function has a lot of connection when we look at the algebraic perspective with the modular theory of Tomita Takesaki. What we have used is the notion of groupoid, the set of measurable sets, and the family of all equivalent measures with respect to this R measure for introducing the Schwinger's picture of quantum mechanics. What I'm now using is a fact that in the class of R measure, there is always one which is invariant when we take the inverse. With this measure, what we can construct actually is a sort of bilinear functional on the pairs of sets, of conditional sets, propositions, simply assigning a number, the measure of the set which we have constructed for the relation of conditionality. This is a positive functional, bilinear, as I was telling you, and symmetric. This functional is defined as the coherence functional, which was introduced, this type of functional were introduced by Gell-Mann and Hartel in their paper on the coherent history and consistent history approach to quantum mechanics, and also were generalized also by Schwinger, by Sorkin in his approach to quantum mechanics in terms of a quantum measure theory. In this setting, this decoherence function appears as generalized conditional probability. It's a measure of the conditionality in this sense. As I was telling you, this decoherence function allows to introduce a grade 2 measure, which is a generalization of a measure which is not additive. Actually, the deviation from additivity is what is introduced an interference functional. However, this grade 2 measure satisfy a generalized additivity when we consider tripoles of sets. This is the Sorkin's interpretation of grade 2 measure is connected with this history approach to quantum mechanics, and is based on preclusion. I will not enter the details because it's a completely different setting. What I wanted to stress is just that this type of object emerge when we consider this type of relation in a natural way. Using measure on the groupoid, we are obtaining grade 2 measure on the space of objects. So another way to describe the same functional is when we consider the convolution product of function on the groupoid. This again is an expression of the composition law on the group, and what we can do is to construct from this, using this convolution product, that this involution is a von Neumann algebra acting on the space of quadratic function or square integral function on the groupoid. The property that I have is that the convolution of characteristic function allows us to give the characteristic function of the product of the two sets. Okay, now if we have an R measure, what we can do is to introduce actually a state on this von Neumann groupoid algebra. And the previously defined decoherence functional can be interpreted now as the scalar product, the GNS Hilbert product in this setting. And the zero set, the measure set that have zero grade to measure, according to this definition, are just elements in the Gelfand ideal, supporting the idea of a preclusion interpretation of quantum mechanics in this sense, of quantum measure. Okay, just to conclude, what I've presented is a conditionality relation in groupoids. Using the R measure and the groupoid, we have been able to construct the decoherence functional, and this has been connected via the convolution product also to states and GNS Hilbert product. What to do? Well, first of all, we are going to see if we can connect this description with the model interpretation of quantum mechanics, and also with the conditional logic that we discovered exists in the literature. It was introduced by Stolnaker, but we are looking for more connection in these sets. Okay, so thank you for the attention. If there are any questions.
Okay, so there are any questions from the audience?
Please, can you explain why groupoid is completely central in your...
The idea is that instead of having only the notion of property of a system, we are looking more to transition as departure point for developing statistical interpretation. So like, this was the idea of Schwinger, that not starting from the being, but considering also the becoming at the same time, being and becoming. And this is more or less the idea that is behind this approach, philosophically.
So you consider a groupoid structure for your logic. Is there any interest to use a categorical point of view and to introduce Toposis to develop more general point of view?
Actually, we were thinking of this. This is just a first preliminary work, of course. And in this sense, what we use for the groupoid, we use the inverse. In the definition of the conditionality, we use the inverse. But of course, one could use directly target and source without making use of the inverse. We haven't explored if this allows us to give a interpretation in terms of quantum measure or only a different interpretation. But this was an idea. The main point is that to have this type of conditionality, it seems to be enough having source and target and something that allows to connect them. But it's still a work in progress, of course. Thank you.
So any other question? So if not, let's thank this speaker again.